Hi, I'm Ed Sperling. I'm the Editorial Director of Low Power Engineering. I'm here with Chris Rowen, the Chief Technology Officer at Tensilica. Are we getting more specialized with the SoC that goes into devices, or is it still going to be sort of generic pieces as well as non-generic pieces? What's changing there?
Yeah. Well, I think there is a lot of currents at work in the evolution of what goes into the SoC and what degree of specialization or general purpose is really forcing the functional evolution. First of all, the big effect of Moore's Law is that more and more gets integrated onto one chip, and so you get closer and closer to a situation where you have the one chip in the system which defines all of its functionality. So if there's a great diversity of systems, then you'll also see a great diversity of chips. And where you see specialization of systems, that will be reflected exactly in more domain-specific specializations of the chip. So you will see less and less general-purpose processor chips, general-purpose memory chips, general-purpose communication chips. They will be around a particular end platform and a particular set of standards. When you start looking inside, however, I think then you get different currents in specialization and generality. Because I think when you look at the total function that you might find in a cell phone chip or you might find in a DTV chip, that's where you'll see, well, a 90-10 rule applies, where maybe 90% of the power and the cost may be determined by 10% of the functions, because it's the 10% that you spend lots and lots of time doing. But the flexibility of the platform may be defined by what range of other things, the 10% of the cycles, but 90% of the functions. And that can be much more general purpose. You have a real benefit in a high degree of programmability and flexibility there. And it doesn't have nearly the same impact on power and cost as the optimizations around the 10% of functions.
So why wasn't this done in the past? What's new? What's changed now that's different from before?
I think there's two things that have changed. First, I think that the technology has developed to make it much easier to choose the degree of specialization. That is, to start from a general purpose processor and then to make it more and more highly tuned for a particular set of tasks, or to take a general purpose interconnect and make it more and more tuned for a specific traffic pattern. So it has become more practical for the average engineering team to turn the knob on specialization versus generality. I also think that the pressure to do it wasn't as great. When you didn't have everything battery operated with days of battery life expected, when you didn't have fanless, noiseless systems as the norm, then people could throw general purpose chips and just have unlimited amounts of computing power that came from throwing tons of silicon at it. Well, you can't afford to in these mobile platforms or some of these very high volume, billion unit platforms to have anything extra, and therefore you really have to confront the question of what is exactly the right balance of specialization and generality that you need in a platform.
Because a DSP is so programmable, you have large fluctuations in terms of how efficient this might be, how much processing it's going to do, and how software might run on this chip versus another chip within the SoC. Does that make it harder to integrate and deal with all the power issues?
Yes, I think the integration problem does change, and it changes, I think, in two ways. First of all, there's what you could call the Moore's Law effect. There are just more subsystems in a chip because you can do it. You can build the 100 million gate, 200 million gate chips pretty easily, and so it's quite natural that you would integrate wireless and security and audio and video and general purpose apps processing and other things all together on a single piece of silicon. And those are diverse, and typically no one design team has all of the capabilities to do those themselves. And so there's more coordination between different teams and more insourcing of IP from IP specialists or vertical application specialists.
DSPs have a reputation for being very programmable, but what are the benefits when you're dealing with a very complex SoC?
The benefits are you can run a very wide variety of algorithms. You can cover everything you can think of, and you have a very good chance of covering everything you didn't think of, during the initial architectural phase. And we typically find that with a well-designed DSP instruction set, there are all kinds of novel ways to use those existing instructions to do computations at very high throughput that you didn't even conceive of before. And so it means that you can have an insurance policy, you can have inherent future-proofing in an architecture by having this kind of general purpose programmability. DSPs are also very different from traditional CPUs in that they take advantage of the inherent high degree of parallelism you find in these computational codes. So it's not unusual to be able to do 50, 100, 200 RISC operations per cycle in one of these high-performance DSPs per core. And then you have the added benefit that you're typically able to take advantage of multi-core more easily in DSP-style applications even than in traditional CPU or traditional microprocessor applications. So there's all of this latent parallelism that's there to be exploited, and programmable DSPs have really become very, very effective at finding that and making that power of the DSP readily accessible across this broad span of numerically intensive computations.
Does it make it more of a challenge to integrate with the rest of the SoC? Because you may have functions that if you did them in one system might be less efficient, or the DSPs might run more because they are more efficient. As a result, your power equation may change for the entire power budget of the chip.
Well, there certainly are some inherent challenges when you're taking on these computational tasks. When you're trying to do hundreds of operations per cycle, you have some inherent challenges with providing enough memory bandwidth to satisfy that computation. You have typically more demands on power management, because the difference between the minimum power and the maximum power of a single processor is greater when it's switching between doing no work and doing hundreds of operations per cycle. And so that has to be taken into account. But in some of the essential ways, like how do you hook it up to a bus, how do you hook it up to debug, how do you go about programming it, a DSP looks very much like the very familiar general purpose processors that people already have. They use the same kind of buses generally, though they may push the performance requirement higher. They're going to use the same sort of on-chip networks. They're going to use the same debug facilities. They're going to use the same kind of compiler tools and desktop software development environments. So in many ways, they don't look very different. But yes, the computational challenges, which are inherent, are still there. Those computational challenges are in some sense even tougher to work with when you're trying to solve those same computational problems just by creating new blocks of RTL. That's really tough.
Another piece of this has to do with the software, and software on a very specialized processor could potentially be much more efficient than it could be on a general purpose processor, right?
Yes, and I think that we find that that's part of the continuum of choices as people decide how far to optimize a processor. There's clearly a fundamental trade-off, even within DSPs, of general purpose versus specialized instruction sets. And you often can get a factor of 2 or a factor of 3 advantage in specialization over a very good general purpose DSP if you say, I'm just going to limit its vocabulary to only the set of operations that I think I'm really going to need. So yeah, are those more challenging to program? Not really within the space that you have defined for them, but if you try to push the envelope a little bit and carry it into other areas, then that specialized DSP can be more challenging to program, because the general purpose DSP has the compiler support, the automatic vectorization. It has a number of things that might be unnecessary in that narrowly specialized core. And so it's part of the trade-offs that people make, where you have RTL design at one extreme, you have specialized DSPs, which we could call data plane processing units. you have general purpose DSPs, and then you have sort of general purpose gigahertz processors that are not all exactly equivalent, but they're all methods that people have used in computationally demanding functions.
Will the ratio remain the same on an SoC between the number of general processors or very specific processors, or is it going to change?
I think that they're clearly increasing, and they're increasing for two reasons. First, there are functions that have been implemented in the past as hardwired blocks, hardwired FFTs, hardwired error correction units, hardwired security state machines, which are migrating from being hardwired to be more programmable because people have a clear sense that they need programmability to build enough flexibility into the platform. There is also the fact that we're attacking harder problems. If you look at the evolution, for example, of cellular wireless bit rates, we've gone in 10 years from needing to deliver a few hundred kilobits per second to needing to deliver a few hundred megabits per second of downlink speed. So you've got a 1000x increase in the raw rates. And some of the computational tasks that you need to do are increasing faster than the bit rate. And so you see this up to 1000x or more increase in the computational demands. And that means that you need to have more total computational power. And given that DSPs, specialized or general purpose, are often the most convenient way to do it, and certainly efficient enough in almost all of these applications, that we do see this rapid growth. And we've seen it, I think, within our own direct experience, where the typical number of DSP cores and engines that people are using are growing from 1 or 2 to 10 or 20 over just 1 or 2 generations of SoC platform.
One of the big changes that's going on right now is we're starting to really mesh big data with little data. The little data being the kind of stuff that you have on your smartphone, the big data being the kind of stuff that was sitting in a cloud or in a data center. That seems to be changing now. How is that all going to affect what we're doing in design?
Yeah, I think that the issues of big data are both interesting and pervasive. I think that a lot of what we've seen in the smartphone revolution is not just that you get access to the static internet, but you're getting access to so many individual experiences, whether it's social media or access to databases. Just take traffic as a way to direct how people commute. It's a big impact, and certainly the Googles of the world have done a wonderful job of figuring out how to gather and farm that big data. But big data has an implication all the way down to the device. It's not just about the user interface to get access to it, but it parallels exactly the kind of computational rates that need to be pulled down onto the device as well. It isn't just that you need a thin pipe to get at the big data. You need a much fatter pipe, and in order for you to have the illusion that it is truly interactive, you need to do much more processing locally. And the evolution of much smarter voice recognition on the cell phone itself, or much better noise reduction, or much better image processing for gesture, is actually an important parallel and a tie-in to what's happening in big cloud database. So big data is not just a cloud phenomenon. Big data characterizes how we are doing so much more computation that is interacting more tightly with both your own local experience, what's coming in through your camera lens and microphone, how it gets out via fat pipes to the cloud, and what's done with the data out there in the cloud.
Chris Rowen, thank you very much for your time.
Thanks, Ed.